Welcome to advanced course on advanced power electronics. So we'll cover today three-phase voltage source inverters. So this is typically a three-phase voltage source inverter for variable frequency drive. And then three-phase inverter, if you look into, typically they are used, three-phase inverters are normally used in high power application. And three single half or full bridge can be connected in parallel to form a three-phase inverter. So the transformer primary winding must be isolated from each other, where the secondary windings may be connected in star or delta. The transformer second is normally connected in delta to eliminate tuple and harmonics appearing on the output voltage. This arrangement requires three single-phase transformers, 12 transistors and 12 diodes. So if the output voltage of single-phase inverters are not perfectly balanced in magnitude and phase, the three-phase output voltage are unbalanced. So this is three-phase inverter with three single-phase inverters. This is also called open winding arrangement, typically of the three-phase inverter. Then this is another three-phase bridge inverter. So a three-phase output can be obtained from a configuration of 6 transistors and 6 diodes as shown in the previous figure. And two types of control signals can be applied to the transistor: 180-degree conduction or 120-degree conduction. And 180-degree conduction has a better utilization of the switches and is preferred method. And this circuit topology is often known as three-phase bridge inverter and used in many applications. Coming to applications of three-phase voltage source inverters, so the typically in the variable frequency drive for induction motor control, as you see typically the scalar control of induction motor. It's also used in DFIG in wound rotor induction, used for doubly fed induction generator, for very wide, around 75% industry are manufacturing this, have a specific advantage that the rating of the converter reduced to around 35%. And then typically the variable frequency control of power synchronous motor. Then the closed loop control of power brushless DC motor, which are used very extensively, fed from single phase for a large number of applications, including like a ceiling fan and many other applications. Then the VSI voltage source converter fed synchronous reluctance motor. Then the synchronous motor. And then VSI fed multi-phase induction machine and the UPS, uninterruptible power supply, very extensively used for many applications. Then the typically for DSATCOM, for distribution network, for reactive power compensation, load balancing, and harmonic elements and neutral current compensation. And then dynamic voltage restorer, also called series kind of active filter. Then unified power quality conditioner, where the voltage are also regulated and voltage harmonic, current harmonic both are elemented, as well as voltage regulated as a combination of STATCOM and DVR. And then static compensator for transmission network for providing the large reactive power. Then the static series compensator as a fax device for transmission system. Then unified power flow controller, for control of power flow, which can reverse even the direction of power flow by injecting appropriate voltage. And then voltage source inverter in picohydro plant for regulating the frequency and voltage at the point of common coupling in isolated system or standalone system. Then the wind energy conversion system for different kind, and typically in a doubly fed induction generator for wind power generation. Then the typically for power synchronous generator for wind power generation. Then power brushless generator for synchronous generation, and then induction generator for wind power generation. Then shunt active filter for power quality improvement, and then series active filter for voltage harmonic compensation and unbalanced voltage regulation. And then in HVDC, voltage source converter based HVDC system is also called HVDC Lite, as well as by the ABB, and HVDC Plus by the Siemens. So we use voltage source converter certainly for high power. So now coming to three-phase voltage source converters classification. These three-phase VSI are classified like square wave switching and pendulum switching. And these are also classified in square wave switching, which again classified 180-degree conduction, 120-degree conduction. And the 180-degree conduction of VSI So this typically you can call it the device conduct for 120 degree. For each transistor conduct for 180 degree, the 3 transistors remain on at an instant of time, one from each phase. So when transistor Q1 is switched on, the terminal A is connected to the positive terminal of the DC bus of the input, and when the transistor Q4 is switched on, the terminal A is brought to the negative terminal of the DC source. So this is typically 3-phase inverter with equivalent circuit for 3-phase star connected resistive load. How it is usually go for in different modes of switching. Phase voltage for 180 degree, conduction for 60 degree, 120 degree and 180 degree. And these are the simulated waveform line voltage and currents of 3-phase VSI for 180 degree conduction with the star connected resistive load. Then this is simulated waveform of phase voltage and current of 3-phase VSI for 180 degree conduction with star connected mode. So now coming to 3-phase voltage source bridge converter, during the mode 1, when 0 to pi by 3, R equivalent is R plus R by 2, that is 3R by 2, and I1 is Vs upon Req, that is 2 by 3 Vs upon R, and Vn is equal to Vcn equal to I1 R equal to Vs by 3, and Vbn equal to minus I1 R, that is minus 2 Vs by 3. And during the mode 2, that is pi by 3 2 by 3, R equivalent to R plus R by 2 equal to 3 by 2 R, and I2 equal to Vs upon Req, that is 2 by 3 Vs upon R. So Vn is I2R, that is 2 by 2 Vs by 3, and Vbn equal to Vcn, that is minus I2R by 2 or equal to minus Vs by 3. So during mode 3, that is 2 by 3 to omega t 2 by 3 to pi, that is R equivalent to R plus R by 2, that is 3 by 2 R, and I3 is Vs by Req, that is 2 by 3 Vs upon R, and Vn equal to Vbn, that is I3R by 2, that is Vs. Vs by 3 and Vcn is equal to minus I3R equal to minus 2 Vs upon 3. So now coming to typically the instance line voltage, line to line voltage VAB can be expressed as a Fourier series. VAB equal to A0 by 2 plus n equal to 1 to infinity, bracket n cos n omega t plus bn sin omega t. So due to the square wave symmetry along the x-axis, both A0 and n are 0. Assuming symmetry along with the y-axis, omega t equal to pi by 6, we can write the Bn equal to 1 upon pi and minus pi by 6 to minus 5 by 6 to minus pi by 6 minus Vs sin n omega t d omega t, and pi by 6 to pi by 6 Vs sin n omega t d omega t equal to 4 Vs upon n pi sin n pi by 2 into sin n pi by 3. So recognize that VAB is the phase shifted by pi by 6, and then even harmonics are 0. To give the instance line to line voltage VAB for star connected load, VAB equal to n equal to 135 to infinity and 4 Vs upon n pi sin n pi by 2 sin n pi by 3 and sin n in bracket omega t plus pi by 6. So both VBS and VCA can be found out by phase shifting VAB by 120 degree and 240 degree respectively. So VBC equal to n equal to 135 to infinity 4 Vs upon n pi sin n pi upon by 2 sin n pi by 3 and sin n in bracket omega t minus pi by 2, and Vcn equal to n 125 to infinity 4 Vs upon n pi, that is sin n pi by 2 sin n pi by 3 and sin n in bracket omega t minus 7 pi by 6. So coming to line voltage RMS can be found out PL equal to in bracket 2 upon 2 pi 0 to 2 pi by 3 Vs square d omega t, square root of that is under root 2 by 3 into Vs, that is 0 to 0.8165 Vs, and the RMS nth component of the line voltage is VLN equal to 4 Vs upon root 2 n pi sin n pi by 3, and for which for n equal to 1 give the RMS fundamental voltage line voltage, that is VL1 equal to 4 Vs sin 60 upon root 2 pi, that is equal to 0.7797 Vs, and the RMS value of line to neutral voltage can be found out from the line voltage, that is Vp equal to VL upon root 3 and equal to root 3 Vs upon 3 equal to 0.4714 Vs. In case of RL load, you can see how the phase voltage is there from varying from Vs by 2 to Vs by 3, and how the current, because of inductive effect, the current try to go closer to the sine wave, which provides the filtering effect. So with the resistive load, the diodes across the transistor have no function, but if the load is inductive, the current in each arm of the inverter will be delayed to its voltage as shown in the above figure. So when transistor Q4 is off, the only path for the negative line current IA is the through D1. So for your star connected load, the phase voltage is Vn equal to VAB under root 3 with a delay of 30 degree. The positive sequence n equal to 1, 7, 13, 19 and a phase advance of 30 degree for a negative sequence n equal to 5, 11, 17, 23 with respect to VAB. So V capital N equal to infinity for pi 4 Vs upon root 3 and pi into sine and pi by 2 sine and pi by 3 into sine and omega t pi by 6 plus minus pi by 6. Similarly VBN and n equal to 1 to infinity 4 Vs upon root 3 and pi sine and pi by 2 sine and pi by 3 into sine and in bracket n omega t minus pi by 3 plus minus plus pi by 6 and VCN equal to n equal to 1 to infinity 4 Vs upon root 3 and pi sine and pi by 2 and pi by 3 sine in bracket sine and in omega t 7 pi by 6 and minus plus pi by 6. So the line current for RL load is given by I equal to n equal to 135 to infinity and in bracket 4 Vs upon under root 3 and pi further under root R square plus n omega L square and sin n pi by 2 sin n pi by 3 into sin n in bracket omega t plus pi by 6 minus plus pi by 6 minus theta and where theta and tan inverse n omega L upon R. So coming to three phase VSI 180 degree conduction star connected resistive load. These are typically you can call it mode 1, 2, 3, 4, 5, 6 phase A voltage, phase B voltage and then according line voltage and typically the line current because it's star connected line current phase currents are the same. So three phase VSI 180 degree conduction star connected resistive load. As a summary, RMS line voltage is 0.78 VDC. RMS line voltage that is root 3 VDC by root 3 line RMS line current root 2 VDC upon 3R and RMS phase voltage root 2 VDC upon R and RMS phase current root 2 VDC upon 3R and power is 3 into root 2 VDC by 3R square into R. And this is typically for three phase VSI 180 degree conduction for delta connected resistive load for all mode 6. Phase voltage, line voltage, phase currents and line voltage and line current are given in terms of typically for resistive load. Similar, so these are the waveform of the VSI 180 degree conduction delta connected resistive load. As you can see, all the line voltage, then line typically phase current, and then your phase voltage and typically the phase current. So this is the simulated waveform for line voltage and current of three phase 180 degree conduction for delta connected resistive load as we discussed in the different mode. I mean 3 phase line voltage and 3 phase you can call it phase current. And these are simulated waveform of phase voltage and current of 180 degree conduction with delta for typically the phase voltage and the phase current. So now coming to three phase inverter for 180 degree with the DC supply current. So neglecting losses, the instance power balance gives VS IS equal to VAB IA plus VBC IB plus VC IC, where IA, IB, IC are the phase current in delta connected load, and DC supply current for positive sequence is given by IST equal to 1 upon Vs in bracket root 2 Va1 sin omega t into root 2 I0 sin omega t minus theta 1 plus root 2 V01 sin omega t minus 120 into root 2 IA sin omega t 120 minus theta 1. Similarly, plus root 2 V01 sin omega t minus 240 into root 2 I0 sin omega t minus 240 minus theta 1. So the DC supply current can be simplified. Is equal to 3 Vs V01 upon Vs into I0 cos theta 1 or equal to root 3 V01 upon Vs IL cos theta 1, where IL equal to root 3, I0 is the RMS load line current and VO equal to fundamental RMS output line voltage. I0 is the RMS phase current and theta 1 is the load impedance angle at the fundamental frequency. So thus if the load voltage and load voltage are harmonic free, the DC supply current becomes harmonic free. However, because of the load line voltage contain harmonic, the DC supply current also contains harmonic. So now coming to one conduction mode of voltage source inverter, three phase full bridge inverter for 120 degree conduction. Each switches conduction for 120 degree and 2 switches remain on at any instant of time. The conduction sequence of switches is 6 1 1 2 2 3 3 4 4 5 5 6 6 7 numbered in a sequence of gating, and the gating signal are shifted from each other by 60 degree to obtain the 3-phase balance voltage. So this is typically the circuit for the 3-phase inverter with the star connected load for 120 degree conduction, and these are the gating signal for 120 degree mode of operation, and these are the waveform of phase voltage of for 120 degree conduction star connected resistive load. As you can see here, line voltage, then you have a line current, then phase voltage and phase current, and these are the simulated waveform of line voltage and current for phase VSI conduction for star connected resistive load. The line voltage and the phase line current, and this is with the typically the star connected simulated phase voltage and currents of 3-phase. So now coming to 3-phase bridge inverter with the 120 degree mode. So you have a mode 1. I mean, when you have a typically 2 phases are connected, 1 phase of 1, and then second AC phase conduct and then BC phase conduct. So coming to during mode 1 from omega t 0 to pi by 3, transistor 1 6 conduct. So Vn equal to Vs by 2 and Vbn equal to V minus Vs by 2, then Vcn equal to 0. So mode 2 pi by 3 2 by 3, transistor 1 conduct. So Vn equal to Vs by 2, Vbn equal to 0, Vcn equal to minus Vs by 2. So during mode 3 from 2 pi by 3 to 3 pi by 3, for transistors 2 3 conduct, and Vn equal to 0, Vbn equal to Vs by 2 and Vcn equal to minus Vs by 2. So the instantaneous line to neutral voltage Vn, Pn, Cn can be accessed in a Fourier series. Vn equal to n equal to 135 to infinity 2 VDC upon n pi sin n pi by 3 sin n bracket omega t plus pi by 6. Similarly, Vbn equal to n 135 to infinity 2 VDS upon n pi sin n pi 3 and sin n omega t by minus pi by 2. Similarly, Vcn equal to n 135 to infinity 2 VDC upon n pi sin n pi by 3 and sin n in bracket omega t minus 7 pi by 6. So instantaneous line to line voltage VAB can be expressed in Fourier series, recognizing the VAB is shifted by pi by 6 and even harmonics are 0. So VAB equal to n equal to 135 to infinity, that is root 3 Vs upon n pi, that sin n pi by 2 into sin n pi by 3 into sin in bracket n omega t plus pi by 6 plus minus pi by 6. VBC equal to n 1 3 to infinity to root 3 Vs upon n pi, that is sin n pi by 2 sin n pi by 3 and sin in bracket n omega t minus pi by 2 and plus minus pi by 6, and Vcn equal to n equal to infinity to root 2 Vs by n pi sin n pi by 2 sin n pi by 3 and sin in bracket n omega t minus 7 pi by 6 and plus minus pi by 6. So the triplan harmonics would be 0 in the line to line voltage. So coming to line voltage can be find out PL equal to in bracket 1 by pi further bracket 0 to pi by 3 VDC square by 2 square and pi by 3 to 2 pi by 3 VDC square plus 2 pi by 3 to pi, that is VD square by 2 square into d omega t square root of all, that becomes VDC under root 2, that is 0.707 VDC, and the RMS nth component of line voltage is VLN equal to root 6 VDC by n pi into sin n pi by 3, which for n equal to 1 give the fundamental line voltage, that is VL1 equal to root 6 VDC by pi into sin pi by 3 or equal to 0.675 VDC. So the fundamental phase voltage equal to root 2 VDC upon pi sin pi by 3 equal to 0.39 VDC. So this is the typically the for 3-phase bridge inverter 120 star connected load. You can see the for all the 6 mode how the phase voltage is, then typically phase currents, then the line voltage and line currents in terms of DC link voltage and resistive load. Now coming to typically output power, IPH equal to root 6 VDC upon 2 pi r and PO equal to 3 IPH square r, and these are the typically summary. RMS line voltage 0.67 VDC and RMS line voltage 0.707 VDC, RMS line current 0.48 VDC by R and RMS phase current 0.408 by VDC and RMS phase current, that is 0.408 VDC upon R, and power is 3 into 0.408 VDC upon A square into R. And now three-phase bridge inverter a kind of in comparison. That is the advantage of 120 degree conduction is the devices are less utilized as compared to those of 180 degree conduction for the same load condition, and thus the 180 conduction is preferred and it is generally used for three-phase inverter. So for 180 degree mode, the fundamental component of output line voltage is 0.78 Vs and output phase voltage is 0.45. So for 120 degree mode, the fundamental component of output line voltage is 0.675 and the output phase voltage is 0.3898 Vs. So the line to line voltage can be found from VL equal to in bracket 1 upon pi in further bracket 0 to pi by 3 VDC square by 2 square, pi by 2 to 2 pi by 3 VDC square plus your 2 VDC square by 2 square, that is from 2 pi by integral 2 pi by pi d omega t and to power half, so it becomes VDC by root 2, that is equal to 0.707 VDC, and the RMS nth component line voltage VLN equal to root 6 VDC upon n pi sin pi n pi by 3, and for which n equal to 1 gives the fundamental line voltage, and VLN 1 equal to root 6 VDC upon pi sin pi by 3 equal to 0.675 VDC. The RMS value of the phase voltage is same as line voltage, that is VDC by root 2 equal to 0.707 VDC. And these are typically for the three-phase PSI with delta connected load for 1 degree mode operation, all 6 modes, and then the phase voltage, then phase current, the line voltage and line current, all are given in terms of VDC and resistive load. So now coming to as a summary, the RMS fundamental line voltage is 0.675 and RMS line current is root 2 0.707 BDC upon R, and RMS phase voltage is 0.707 BDC and RMS phase current 0.707 BDC upon R, and power is 0.408 BDC divided by R square into R. So coming to three-phase voltage source inverters, pendulum technique. So three-phase VSI in pendulum switching, sinusoidal pendulum, third harmonic pendulum, and space factor pulse width modulation. So coming to sinusoidal pulse width modulation, so this is three-phase inverter, and assumption DC capacitor is very large, so DC link voltage is ripple free, and these are modulating and carrier wave. So we have a typically 3 modulating wave, that is the signal we want to amplify at the inverter output, and we have a carrier wave. So we can call it VCR is carrier wave, triangular wave, and VM is modulating sine wave. So amplitude modulation we define M equal to VM upon VCR, and frequency modulation we define MF equal to FCR upon FM. So we can say how the gate signal are derived from typically this comparison. So you can say VG1 and VG4 for A phase lag, and what is the VAN, the voltage of A phase with respect to the midpoint of this of your DC link, and you can call it how the phase, typically phase A, the two devices are on, and what is the equivalent to the voltage VN equal to D or 0. So now coming to the line to line voltage of VAB. So when we compare like a typically then VMA or VMA, we get a VN and VBN. I mean with respect to the neutral point of, you can call it negative terminal of the DC link, and then subtracting from VN to VBN, it comes VAB, and you get the typically unipolar voltage with pulse width modulation to giving a fundamental dominant and harmonics very less. So you can call it waveform and FFT. So these are typical line voltage, then it is a voltage with respect to neutral. So line voltage here I have a 92% TAD, and for this modulation index 0.8 and MF equal to 15 and FM equal to 60 and CR equal to 900, but the TAD of the current because of inductive effect it becomes 7.73, which is even much lesser than 110. So now switching frequency you can call it like a what is the harmonic analysis for VABN. You can see fundamental and then sideband of your modulation index, typically frequency modulation, and which is 15. So you will find the harmonics of all odd harmonics here, and TAD of course is 92.7%. So similarly here you can call it like how it is the sinusoidal pendulum. TAD varies with the modulation index, so it goes typically very high and then goes typically lower side. So lower order harmonics for N MF minus 2 are eliminated, and VAB1 vary with MA as a linear, and VAB1 maximum is 0.612 VD. And you can see how the different harmonics are there with. Now coming to typically case of overmodulation, so we have a fundamental voltage which increases. Here in overmodulation, certainly we miss some of the switching, as you can see in the waveform, and then we have a, of course, the current which have a typically lower harmonic and a harmonic spectrum. So now coming to the 4 field consideration for low voltage, low value of MF, 12 minutes the even harmonics, a synchronized pendulum should be used, and MF should be an odd integer. So moreover, MF should be a multiple of 3 to cancel out the most dominant harmonics in the line to line voltage. And for large values of MF, the amplitude of amplitudes of some harmonics due to asynchronous pendulum are small. When the inverter supplying a load such as an AC motor, the subharmonics are 0 or close to 0 frequency. Even though the small in magnitude will result in a large current that will be highly undesirable. Therefore, asynchronous pendulum is avoided. So during overmodulation, MF greater than 1, regardless of the value of MF, the condition pertinent to the small MF should be observed. So these are generalized harmonics. You can say generalized harmonic of line voltage for large and odd harmonics with the modulation index, and these are the harmonics plus minus to the magnitude. And you can interestingly observe that some of the harmonics are reasonably dominant. In that case, like as you can see, 4 MF plus minus, that's typically even a 2 MF plus minus 1, that is order of E, or typically even much higher than fundamental, as you see for the lower modulation index. So you cannot say that even your many harmonics are reasonable, for different modulation index. So coming to linear modulation, MA equal to less than 1. In this region, the fundamental component in the output voltage varies linearly with the amplitude modulation, MA. So VN1 equal to MA BD C by 2 into root 2, and VAB1 equal to MA into root 3 VD upon 2 root 2 equal to 0.612 VD. Our modulation in this region, MA greater than 1. The fundamental component in output voltage do not vary linearly with the amplitude modulation ratio MA, and more sideband harmonics appear centered around the frequency of harmonics MF and its multiple. So for MA between 1 to 3.24, the fundamental component of line voltage given 0.612, 0.78 VD, and over modulation, that is MA greater than 3.2, it acts as a square wave inverter. The fundamental component of line voltage VAB1 equal to 0.78 VD. And this is the typically how the, when call it the for frequency modulation 3, how the modulation index goes square wave at with the 3.2 or up to 1, it's only the linear variation. You can see the how with the it goes with the square wave for typically above your MA equal to 2.21. So coming to now the restriction, coming to sinusoidal pendulum with the 0 sequence signal injection. So restrictions for MA less than 1 can be relaxed if the 0 sequence signal is added to the modulating signal before they are compared with the carrier wave. So we add here typically the signal corresponding to V0. So the addition of 0 sequence reduces the peak amplitude of the resulting modulating signal VCA, VCB, VCC, while the fundamental component remain unchanged. And this approach expands the range of linear region as it allows the use of modulation index MA up to the 2/3 without getting into the over modeling region, as you can see here. So now coming to third harmonics pendulum. So typically the sine triangular pendulum can be used, but it may produce high losses during the transient. Better to use the sinusoidal triangular method, and a small percentage of third harmonics can be added to the reference voltage to increase the fundamental component and use better the converter. So typically third harmonics injection, how we are adding the third harmonics along with the fundamental, and then typically comparing with the carrier wave. So VM1 is less than VCR, so no load harmonics are produced, and VM1 equal to greater than VCR, so fundamental voltage increase. So third harmonics 0 sequence to appear in VN and VBN, and no triplet harmonics in the line voltage VAB, that is VAB equal to VN minus VBN. So now coming to the modulating or reference signal is generated by the injecting selected harmonics to the sine wave, and thus the reference AC waveform in the third harmonic pendulum is not sinusoidal but consists of both fundamental component and the third harmonic component. So as a result, the peak to peak amplitude of resulting reference function does not exceed the DC supply voltage Vs, but the fundamental component is higher than the available supply Vs. So the presence of exactly the same third harmonic component in each phase results in an effective cancellation of third harmonic component in the neutral terminal, and the line-to-line neutral phase voltage VNBV and VCN and are small sinusoid with the peak amplitude of Vp equal to Vs by root 3 equal to 0.57735 Vs, and this approximately 15.5% higher in amplitude than the achieved by sinusoidal pendulum, and therefore the third harmonic pendulum provides the better utilization of the DC supply voltage than the sinusoidal pendulum does. Now coming to 60 degree PWM. So in 60 degree pendulum, the 60 degree pendulum is similar to the modified sine pendulum. The idea is behind 60 degree pendulum is to flat top the waveform for 60 degree to 120 degree and 240 to 300. So power devices are held on for 1/3 of the cycle when the full voltage and have reduced switching losses, and all the triple and harmonic third, 9, 15, 17, 21 are absent in the your 3-phase voltage, and the 60 degree pendulum creates a large fundamental to root 3 and utilize more of the available DC voltage, and phase voltage Vp equal to 0.57735 Vs and line voltage VL equal to Vs, and then the sinusoid pendulum. The output waveform can be approximated by the fundamental and the first B term. So this is typically how flat top waveform, when you can analyze it with the 6 degree the fundamental and third harmonics into it. So now coming to space factor PWM. So space factor modulation is quite different from the PWM methods, and with PWM the inverter can be thoroughly thought of as of 3 separate push-pull diverge stages which create each phase waveform independently, and SVM however treats the inverter as a single unit. Specifically, the inverter can be driven by 8 unique states, and modulation is accomplished by switching the state of the inverter, and the control strategy are implemented in digital signal system. And SVM is a digital modulating technique where the objective is to generate pendulum line voltages that are in average equal to a given or a reference to load line voltage. So this is done in each sampling period by properly selecting the switch states of the inverter, and the calculation of appropriate time periods for each state, and the selection of the states and their time periods are accomplished by the space vector transformation. So this is typically switching states, summing for 3 phase with the star connected load, and you can see the switching state lag A, lag B, lag C, and SA on and S4 on. So you have a typically what is V and VD equal to 0, positive switching state is positive or negative kind of, and here you have a switching states of typically 3 phase. So we have here the 8 switching states on state. 8 switching states are there with the 3 phase inverter. That PPP means you can call all 3 upper devices are on, and 0 0 your all 3 lower devices are on. These are the 2 additional vector 0 vector in addition to 6 vector which are of 60 degree each, used already for typically for other 120 degree and 180 degree mode operation, but the 2 0 vector introduced in space vector modulation only. So now coming to the space vector diagram, the active vectors are 0 1 to 6 as shown here with the notation, and then 0 vector is V0 and 6 vector 1 to typically 6, and you can see these 6 vector and 0 vector at the 0 point like. So now coming to space vector, 3 phase voltage VAO plus VBO plus VC equal to 0, and 2 phase voltage V alpha V beta comes 2 by 3 in matrix, and the function of VAO VB VCO. So it comes cos 0 cos 2 y by 3 and cos 4 y by 3, similarly sin 0 sin pi 2 y by 3 and sin 4 y by 3. So space vector representation becomes V as a phasor as a function of time equal to V alpha plus J V beta, and from these two above 2, so V comes 2 by 3 VAO e to power 0 and VBO e to power 2 by 3 and VCO e to power 4 by 3, where the Ex equal to cos x plus J sin x. So now coming to switching state P0 0, that is S1, S6 and S2 are on. So we get a VO equal to 2 by 3 VD, VBO equal to 1 minus 1 by 3 VD, and VCO equal to minus 1 by 3 VD, and V1 equal to 2 by 3 VD, e to power j and e to power 0, and similarly vk, we can define vk vector, we can do by 3 vd to power j k minus 1 pi by 3, where k is 1 to 6 as shown in the diagram. So now coming to active and zero vector, the active vector and zero vector are 2, the resultant switching states p and 0 0 are the zero vector, in addition to the other vector you can see here typically. The zero vector gives 0 voltage, and but there are two switching states we can be used here, and see many six vector, how the on state switch and how the your vector definition. So now coming to reference voltage, V reference. The definition is V reference equal to V reference e to power j theta, rotating in space at omega angle, so omega equal to pi f, and angular displacement theta equal to 0 to t omega dt. And now relationship between V reference and VAB. So V reference is approximated by two active and zero vectors, and V reference rotates on one direction. VAB completes one cycle, and length of V reference corresponds to the magnitude of VAB. So now coming to dwell time calculation, so volt second balancing is required. So V reference TS equal to V1 TA plus V2 TB plus V0 T0, and TS equal to TA plus TB plus T0, and TA, TB, and T0 is the dwell time for V1, V2 and V0, and TS is the sampling period, and space vector V reference equal to V reference e to power j theta, V1 equal to by 3 Vd, and V2 equal to 2 by 3 Vd e to power j pi by 3, and V0 equal to 0. So from now coming up from the equation, then so real and imaginary parts separately. So V reference cos theta TS equal to by 3 Vd TA plus 1 by 3 Vd TB, and imaginary part V reference sin theta TS equal to 1 by root 3 Vd TB. And typically solving for dwell angle, so TA equal to root 3 TS V reference by Vd into sin pi by 3 minus theta, and TB equal to root 3 Vt TS V reference by Vd into sin theta, and T0 equal to TS minus TA minus TB, that is theta varying from 0 to pi by 3. Now coming to the V reference location with versus dwell times, so you can say V reference and dwell time with the in the table it is given for different, you can call it the mode like. So now coming to modulation index, so T equal to TS MA into sin pi by 3 minus theta, TB equal to TS MA sin theta, and T0 equal to TS minus TB minus TC, and MA equal to root 3 V reference upon Vd. And coming to modulating range, so V reference maximum is 2 by 3 Vd into root 3 by 2, that is Vd by 3, and MA max is 1, so modulation range is 0 to 1. So now coming to switching sequence design, the basic requirement is minimize the number of switching per sampling period TS, and implementation transition from one switching state to the next involve only two switches in the same inverter lag. So now typically taking a 7 segment switching sequence, selected vectors DO V1 and V2, dwell times DO DS TS equal to T0 TA plus TB. So you can say total number of the switching is 6 here. I mean for the different, if you divide the period typically in different parts starting from TA TB, how the different states. So you have 0, typically 2 0 vector 0 0 and 12 to reduce the number of switching. And so here undesirable sequence is vector V1 are swapped, and total number of switching goes to 10. So here it switching is only 6 like. So now coming to the switching sequence summary, 7 segment. So here we have a sector, 6 sectors, then we have a switching sequence starting from V0, L0 vector to V1, V2, V3, and up to V0, you go for even 0 vector. So switching sequence for the odd and even sectors are different, and this is typically if we take a simulated waveform, so you can say what the switching vector, what is BAB, then what is BAO, and what is the current typically. For the F1 equal to 60 and FW 900, M equal to 0.696, and TS equal to 1.1. And this is the harmonic waveform and FFT. So this line voltage have a TAD around 80.2%. Typically VO equal to have a 80.2%, and the current have a TAD of 8.37%. And this voltage of course given 80.2% as a harmonic spectrum here. And these are the typically the waveform and FFT for line voltage and that phase voltage and the 80% TAD, and is a variation of typically for even order and order harmonics. How it goes with the typically with the modulation index, and this is the typically a even order harmonics elimination. So type A sequence start from and end with the 000, and type B sequence start from and ends with the P, typically PPP, means all three upper devices are on. So you can just see the even order harmonics are elimination. I will do type A sequence, type B sequence in any space vector diagrams. So measured waveform and FFT. So here the line voltage, you can see clearly the line voltage TID is 80.5%, and here the line voltage TID normalized goes with the typically with the modulation index for 60 Hz and TS equal to 1 by 2 720, and these are the typically sequence A where the switching completely missing in one phase, and switch sequence B where the also switching one phase. So it case 5 sequence space vector model. So coming to this switching sequence of 5 segment, so where we have a typically here the segment 6 segment and switching sequence of given A going to be power, and what are the voltage Vn equal to Vn which becomes 0. So and this is the typically getting signal and line voltage and the current. Typically for frequency 60 and switching frequency 600, modulation index 0.96 and TS equal to 1.1. So no switching for a 120 period per cycle, and low switching frequency but high harmonic distortion. So coming to generalized formula for space vector modulation, the space vector for 3-phase VSI can be given as Vs equal to y3 Vd in bracket SA plus ASB plus A square SC, where A equal to 2 e to power j2 pi by 3, as the phase ABC voltage can be obtained as V equal to 1 by 3 Vd in bracket 2 SA minus SB minus SC, and VB equal to 1 by 3 Vd in bracket 2 SB minus SA minus SC, and VC equal to 1 by 3 Vd in bracket 2 SC minus SC minus SB. So now coming to switch utilization of the 3-phase inverter. So to compare the utilization of switches in the 3-phase inverter, we'll assume that there is a sufficient inductance associated with the load to yield pure sinusoidal output current with an RMS value of I max both in preload and the square wave mode at maximum loading. So Vt equal to Vd max and It equal to root 2 I max. So if VLL1 is the RMS value of the fundamental frequency line to line voltage, then VA 3-phase will be equal to root 3 VLL1 into IU max. So therefore the total utilization ratio of all 6 switches combined is switch utilization ratio, that is equal to VA 3-phase divided by 6 VT IT, that is root 3 VLL IU max 6 VD into root 2 IU max, and that is equal to 1 by 2 root 6 into VLL1 VD. So in PLM region M equal to 9, noting that the maximum utilization occurs at Vd equal to Vmax. So maximum switch utilization ratio is 1 equal to 1 upon 2 root 6 and 3 root 3 upon 2 root 2 MA, and that becomes 1 by 8 MA for the modulation index equal to less than 1. So coming to summary of your modulation technique, like sinusoidal modulation, what is the normal phase voltage like 0.5, then the normalized you can call lot voltage 0.866 and sinusoidal, and typically 60 degree pendulum. Then the third harmonics and space vector modulation, over modulation, and 6 step. So in all cases, it is given phase voltage as well as normalized line voltage and the output waveform. So now coming to DC link current in 3-phase VSI. So due to the fact that the inverter is assumed to be lossless and constructed without storage energy component, the instantaneous power balance indicates that VI into II equal to VAB IA plus VBC IB plus VC IC. So if the load is balanced and inductive and a relatively high switching frequency is needed, the load current becomes nearly sinusoidal balance waveform. So if the AC output voltages are considered sinusoidal and the DC link voltage is assumed to constant VI equal to VI, capital VI, so the expression for the typically for the DC input current can be calculated. So it comes I1T 1 upon I, 1 upon VI in bracket root 2 VO1 sin omega t into root 2 I0 sin omega t minus y. Similarly for plus root 2 VO1 sin omega t minus 120 into root 2 I0 sin omega t minus 120 minus pi, and plus root 2 VO1 sin omega t minus 240 into root 2 I0 sin omega t minus 240 minus pi. So where V0 is the fundamental RMS AC line voltage, I0 is the RMS phase load current, and phi is the inductive load power factor. So the AC link current expression can be further simplified I1t to 3 VO1 upon VI I0 cos phi, or root 3 VO1 upon VI I1 cos phi. So where IL equal to root 3 VI0, I0 is the RMS load line current. So now coming to typically you can say the waveform, how it is the DC link current form and how the harmonic spectrum of this DC link current. So resulting DC link current expression indicate that the under harmonic free load voltage is only a clean DC current should be expected in the DC bus, and compared with the single phase VSI, there is no presence of second harmonic. However, the AC line voltage contain harmonics around the normalized sampling frequency. The DC link current will contain harmonics but around FSN. Now coming to numerical example. So coming to example 1, a 3-phase voltage source converter feeds a RL load of 5 ohm and 0.8 lagging. Calculate the current TAD. So you can see the 3-phase load connected to 3-phase inverter, and typically your phase voltage and line voltage are given here. So given that V equal to 220 volt and impedance is load impedance 4 plus 3J, that is 5 ohm impedance at 0.2 lagging. Now the fundamental current will be I1 equal to V1 upon Z1, that is 220 upon 5, 44 equal to 44 ampere, and harmonic current is given IN equal to V1 upon Zn equal to V1 upon N into 1 upon R plus JXN equal to N V1 upon N under root R square plus XN square. So now since the triplet will be 0, so I3 and 9 will be 0. So from this equation, the dominant fifth harmonic calculated I5 equal to V pi upon Z5, that is V pi upon 5 divided by 1 upon R plus J X5, and this becomes 220 into divided by root 5 under root 4 square plus 5 into 3 square, that becomes 2.83 ampere. So coming to similarly for 7th order and other harmonics calculated, so I7 equal to V7 by Z7, and that is V7 by 7, that is 1 into 1 upon R plus J X7, and 220 upon 7 into under root 4 square plus 7 to 3 square equal to 1.47. Similarly for I11 equal to V11 by Z11, so V11 by Z11 V11 by 11 into 1 upon R plus JX1, putting a value it comes 0.6016, and I13, that is 1 V13 upon Z13, that is V13 by 30, V1 by 13 into 1 upon R plus JX3, putting a value 0, it comes 0.4316. Now the harmonic current is calculated IH equal to I5 square, I7 square, I11 square, I13 square equal to 3.273 ampere, and now current TAD is IH upon I1, that is 3.27 upon 44, that is 7.44 degree, and voltage TAD for this 6 pulse is 31%. So now coming to second example, a 3-phase bridge inverter has a star connected load of 5 ohm and L equal to 23 millihenry. The inverter frequency is F0 equal to 60 Hz, and the DC link voltage Vs equal to 220. The inverter is operated in 180 degree conduction mode and express the instance line to line voltage VAB and the line current IA in case of ODC, determine the RMS line voltage VL and the RMS phase voltage BP. So solution is Vs equal to 220, R equal to 5 ohm, L equal to 23 millihenry, F0 equal to 60 Hz, and omega equal to 2 pi into 60, so that is equal to 377 radian per second, and the instance line to line voltage is given by expression VAB equal to N135 to infinity into V4 Vs upon N pi sin N pi by 2 into sin N pi by 3 into sin N bracket omega t plus pi by 6, and hence putting the value VAB equal to 242.58 sin 377 t plus 30 degree minus 48.53 sin 377 t plus 30 degree minus 34.66 sin 377 plus 30 and 22.07, that is sin 11 in bracket 377 plus 30 and plus 18.66 sin 377 plus 30 degree minus 14.27 sin 17 bracket 377 plus 30 degree plus so. Now coming to load impedance for nth harmonic Z n equal to under root R square plus N I square at the angle of tan inverse and WL upon R, so that is under root 5 square plus 8.67 N square at the angle of Z inverse tan inverse 8 in bracket 8.67 n upon 5. So dividing the voltage expression by load impedance, the current can be calculated. Ia equal to 14,377 minus 60 degree. Similarly, 0.464 sin 5 into 377 plus 36.6 degree. Similarly, minus 0.33 sin 7 into 377 plus 9. Similarly, 0.13 sin 11 3 into 377 t plus 213 degree. Similarly, 0.1 sin 13 into 377 plus 272.5 degree minus 0.06 sin 17 into 370 t plus 391.9 degree. So line to line voltage given by VL equal to root 3 Vs, that is 0.8165 equal to 179.61, and hence the phase voltage Vp equal to VL upon √2. Putting value, it comes 103.71 volt. So coming to example 3, a three-phase bridge inverter operated at in 180 degree mode conduction mode has a star connected RL load of R equal to 10 ohm and L equal to 15 millihenry, and the inverter frequency is F equal to 50 Hz, and the DC supply voltage is Vs equal to 400 volt. So determine the RMS line voltage VL1 and fundamental frequency, and the phase voltage at fundamental frequency VP1 and the TAD. The solution is Vs equal to 400, R equal to 10, L equal to 15 millihenry, F0 equal to 50, and omega 2 pi into 50, that is 314 radian per second. The RMS value of nth harmonic component of line voltage is VLN equal to 4 Vs upon √2 n pi sin n pi by 3, and putting n equal to 1 for fundamental component, VL1 equal to 4 Vs sin 60 upon √2 pi, that is 0.7797 Vs, or VL1 equal to your 311.88 volt. And hence the phase voltage at fundamental frequency can be calculated Vp1 equal to VL1 under √3, that's 311.88 divided by √3, 180.06, and now the harmonic content is calculated VL square minus VL1 square. Putting value, it comes 0.2423 Vs, and the TAD can be found out typically from this, so it comes 31.08%. Now coming to example 4, a three-phase bridge inverter operated in a 180 degree mode has a star connected RL load of R equal to 21 ohm and equal to 89 millihenry. The inverter frequency is F0 equal to 50 Hz, and the DC input voltage is Vs equal to 300 volt, and determine the load power, average supply current, the average and RMS value of current through power summing procedure. Ignore all the component above 7 harmonic. So solution is Vs equal to 300 volt, R equal to 21, L equal to 89 millihenry, F0 equal to 50, and omega is equal to pi into 50, that is 314 radian per second. The expression for instance line voltage VAB equal to n to 135 to infinity for Vs upon n pi sin n pi by 2 and sin n pi by 3 into sin n in bracket omega t plus pi by 6. So putting value for VAB, all these values, so it comes like a VAB equal to 330.8 sin 314 t plus 30 degree minus 66.16 sin 5t by 314 plus 30 degree minus 47.56 sin 7 in bracket 314 t plus 30 degree. The impedance is Zn equal to under root R square plus n omega square at the angle of tan inverse n omega L upon R, and that comes 21 square plus 2 27.95 n square at the angle tan inverse 27.95 n upon 21. Hence the expression is for the current is I equal to 9.46 sin 314 t plus 30 degree minus theta 1 minus 0.468 sin 5 314 plus 30 degree minus theta 5 minus 0.242 sin 70 314 point plus 30 minus theta 7, where theta in the phase corresponding to nth harmonic. So the star connected load, line current and phase currents are same. So IL equal to typical 9.46 square 0.46 square plus 0.4242 square power half divided by √2, that comes 6.7 ampere. Hence the load power is P equal to 3 IL square R, that is 2.83 kilowatt, and the average supply current is IS equal to P upon Vs, that becomes typically to 9.43, and average switch current IQ equal to 9.43 divided by 3, that is 0.14 ampere, and RMS current from the switch is IQ RMS to IL upon √3, that becomes 3.87 ampere. Now coming to example 5, a three-phase bridge inverter is fed from the DC source of DC volt, and the inverter is operated in 180 degree conduction mode, and it's supplying a pure resistive star connected load with the R ohm per phase. Determine the range rating of the transistor. The solution is the transistor current waveform for 180 degree mode conduction for resistive load is shown typically here. It goes from ED by 3, then 2 ED by 3, and then again ED by 3 0, and then similarly it repeats. So transistor peak current is IP equal to 2 by 3 ED by 3, and IRMS will be under root 1 upon 2 pi 0 to pi by 3 ED by 3 d omega t, pi by 3 2 by 3 2 ED by 3 square d omega t, and 2 pi by 3 2 pi EDC by 3R square d omega t, and solving this it gets EDC by 3R, and transistor average current comes I average to 1 upon 2 pi 0 to pi EDC by 3R d omega t plus pi by 2 by 3 2 EDC by 3R d omega t plus 2 pi by 3 pi EDC upon 3R d omega t, and putting the value it comes 1 by 3 2 EDC upon 3R. So maximum voltage the device can handle is the EDC. Considering safety factor 1.5, the device rating are IT greater than 1.5 IP, that is the value of EDC upon R, and VCO equal to 1.5 EDC. So coming to example 6, a 3-phase transistor is pre-generator operating 180-degree conduction mode and supplying the voltage EDC and star connected resistor load. Determine the current waveform for transistor and obtain the rating. So transistor current waveform shown here, that is magnitude EDC by 2, EDC by 2, EDC by 2R with the 0 up to 120 degree, then 180 to 40 degree. So transistor current rating is I RMS equal to 1 upon 2 pi 0 to pi I squared d omega t, that is under root 1 upon 2 pi 0 to pi 3 EDC upon 2 R squared d omega t, and putting the value it becomes EDC by 2 root 3 R, and I average it becomes 1 upon 2 pi 0 to pi 3 EDC upon 2 R d omega t, that is EDC by 2R into 1 by 3, and I peak is EDC by 2R. So maximum voltage across the device is EDC. So it remains between between EDC this up to 1.5, where the 1.5 is a safety factor. Coming to example 7, a 3-phase VSI with the DC link voltage of VD equal to 600 volt operates with sinusoidal freedom at a modulation index of M equal to 8.8. The inverter feeds a balanced load with a line-to-line RMS voltage VLL. So calculate the fundamental peak output voltage VO and also determine the RMS value of PLL. The solution is for sinusoidal freedom. The peak phase voltage is VO equal to MA VD by 2 and VO equal to 0.8602, that's 240 volt. So line to line RMS voltage for a balanced 3-phase system is related to peak voltage. So VLL equal to root 3 VO into 1 by root 2, and VLL equal to putting value 293.92 volt. Coming to example 8, a 3-phase VSI with a DC link voltage of VD equal to 400 volt operates with the sinusoidal freedom at a modulation index M equal to 2.8. Calculate the RMS value of the phase voltage, and if it is controlled by a third harmonics PWM, what will be the phase voltage RMS value? So for sinusoidal freedom, the RMS phase voltage is VRMS equal to MA VD upon 2 root 2, and putting value it comes under 13.13 volt, and using the third harmonic injection, the peak voltage will be 15% more than the obtained by in sinusoidal freedom. Hence the RMS voltage in this case will be 1.15 into 113.13, that is 130.1 volt. So coming to example 9, a 3-phase inverter is operating with a space factor modulated PWM, and the reference factor has a magnitude of 0.7 VD and is positioned in the sector 1 with the DC link voltage VD equal to 600 volt. The switching period is TS equal to 100 microseconds. Calculate the switching times T1, T2 and T0 for the active 0 vector. Consider the angle V reference in sector 1 to be 30 degree. So T1 equal to TS into root 3 V reference sin pi by 3 minus alpha upon VD. So putting value T1 comes 10.5 degree and T2 TS root 3 V reference sin alpha upon VD. So it comes 6.06 microsecond, and T0 equal to TS minus T1 minus T2, that comes around 83.44 microsecond. Now coming to example 10, for an inverter using a space factor PWM, the DC link voltage is VD 500. Calculate the maximum available RMS voltage, compare the maximum RMS voltage achievable with sinusoid. So maximum RMS voltage achieved using a space factor modulation VOS at W equal to 1 by root 2 VDC by root 3, that 204.12, and the maximum RMS voltage possible using a sine pendulum technique is VOS equal to 1 by root 2 VD by 2, that is 176.77 volt, and hence the increase in the voltage using space spectrum, that is 204.12 minus 176.7 divided by 170 into 100, that is 15.47. And these are the unsolved problem which you can show in the similar way, and these are the references which are used for developing this material. And thank you.